Okay, great. So good morning, everyone. It's great to be here. My name is Sohaib. I'm a scientist at the NASA Ames Research Center at Moffett Field, California. And today I will talk to you about quantum algorithms for Hamiltonian simulation. So this broad problem of Hamiltonian simulation, or quantum simulation for short, it really dates back to the original conception of quantum computers, which is often popularly attributed to Richard Feynman, but it was also somewhat independently and somewhat earlier also conceived by the Russian mathematician Yuri Manin. And what they realized is that even though certain quantum mechanical systems could be solved for analytically, and if you're clever enough numerically, for generic quantum mechanical systems, classical computers will inevitably run into a computational cost that scales exponentially in the size of the problem input. And so what they proposed is that one ought to instead use so-called quantum computers or quantum mechanical machines or quantum mechanical devices that you could control and program and manipulate in such a manner that they can mimic or simulate the dynamics of other quantum mechanical systems of interest, such as those that might appear in high energy physics or condensed matter systems and so forth. So you have this rather famous quote by Feynman that if you want to make a simulation of nature, then you better make it quantum mechanical because nature itself is quantum mechanical. And more precisely, what we mean is that is as follows. So Schrödinger equation tells us that given some initial state at some time t equals 0, if your Hamiltonian is, if the Hamiltonian of the system is time independent, and for the purposes of the talk, this is a simplifying assumption that we will make. The methods that I will discuss today can be extended to handle the case of time-dependent Hamiltonians, but for simplicity, we will only consider the time-independent case. So in that case, Schrödinger's equation simply tells us that the future state of the system, psi of t, is given by e to the minus iht times the initial state. So the whole problem of quantum simulation essentially boils down to finding some unitary approximation to that basic unitary e to the minus iht. Now, if somehow we were able to actually engineer that Hamiltonian H itself, then of course we would be done, right? All we need to do is just switch on that Hamiltonian for some time t and let the system evolve according to that Hamiltonian, and that's it, right? But if we had access to such a Hamiltonian, that means that we have access to the system itself. And what we're really doing is letting the system simulate itself. And that's, kind of broadly the idea behind so-called analog quantum simulation. But what we're going to discuss today is digital quantum simulation. So in other words, we will have access to a qubit-based quantum computer, which can only run a certain set of primitive operations, such as the ones you've been hearing about in previous talks, like, single qubit gates and CNOT gates and so forth. And so the idea is that we want to compose those primitive operations in such a manner that their product approximately equals e to the minus iht. And we want to do it in as parsimonious a manner as possible. And sometimes, we might also relax, the condition at the very top line and say, well, okay, we might also make use of some ancillary qubits, right? So in other words, instead of actually epsilon approximating e to the minus iht, we might implement some other unitary that acts, yes?
I was wondering if you make any assumption on what kind of operator norm you're taking, or that?
So typically it's the spectral norm. Oh, so the question is, are we making some kind of assumption about what the norm over here is? Typically it's the spectral norm. And I mean, so the spectral norm, you could think of it as like, what's like the maximum effect it can have on any particular, if you have an operator A, it acts on some state psi. If you act A on psi and, you divide out by the norm of psi, what's the maximum norm that you get, right? So you want, in that particular norm, you want it to be as minimized as possible, right? And we might say that, okay, like, like we, instead of actually implementing e to the minus iht, we might instead apply a unitary that acts on the ancillary register as well as the system of interest. And then, to some epsilon approximation, this produces sort of like an unentangled state. We don't really care what operation it actually implements on this ancillary register. Typically, you might see this condition where V is the identity. But the real thing that we're interested in is applying e to the minus iht on psi. Okay. And the methods that I will discuss today are the Lee-Trotter-Suzuki method, which often goes by the name of Trotterization for short, the linear combination of unitaries method, or LCU, and the quantum singular value transform, or QSVT, which is a somewhat recent development, but I just wanted to, introduce you to that as well. And one thing we won't talk too much about today, but that you will probably hear about in other talks, is encodings, right? So I said at the beginning that we're going to use a qubit-based universal quantum computer. So that means that whatever system that you're actually interested in, simulating, you need to first of all map it onto qubits, right? So that means you need to map operators to qubit operators and states to qubit states, right? So I'll just mention that this can be done, right? So in the case of fermionic operators, for example, you can use the Jordan-Wigner transformation. Other more efficient transformations also exist. In the case of the scalar field, for example, people like to work in this field amplitude basis. And if you also have to map your states to superpositions of bit strings of computational basis states. And so, in the case of fermions, for example, you can map these Slater determinants to occupation number basis elements using, the so-called second quantization approach. But for the purposes of today, we will assume that this has somehow been done. I will like to say that this is often a non-trivial step, and you'll probably get more into it in other talks. We'll basically assume that the Hamiltonian that we consider can be written as a combination of Pauli operators. And one of the nice things about Pauli operators that I'll mention from the very start is that they're both Hermitian and unitary. And this is a property that will, exploit in at least one of the algorithms. And the system and the states of the system are basically just some, superposition of computational basis states. Okay, so now we'll consider n-qubit k-local Hamiltonians, right? So now basically I've written some Hamiltonian. It is a sum of m terms, and each of those HIs are Hermitian operators. They don't necessarily commute with one another. And let me just set terminology here for a little bit. So when I say k-local, I mean a very specific thing, right? So many of you, I imagine, are coming from maybe like a high energy physics background or something. And in quantum field theory settings, typically when we say local operators, we typically mean local in space-time, right? So we mean that, like, things are in some sense geometrically local, that things only interact with stuff that's close by. Even in sort of like discrete many-body settings, you might be used to thinking about things that only interact with nearest neighbor sites or so forth. But in computer science settings, k-local basically just means that even though the full operator might act on n sites, the operator itself is composed of terms that by themselves act on at most k sites, right? So a simple example is this 5-qubit 2-local Hamiltonian, where, I mean, it acts on a total of 5 qubits, but if you look at any one of these terms, it only acts on 2 sites. But those 2 sites don't necessarily need to be geometrically close. They could be very far apart, okay? Okay, good. So from the Baker-Campbell-Hostor formula, we know that the exponential of this Hamiltonian isn't exactly equal to the product of the exponentials of the individual terms because of these commutator terms. Nevertheless, we have this Lee-Trotter product formula that says that if you have if you break up the overall time evolution into a bunch of small time evolutions, t over n, and then compose the product of the exponentials of each of the individual terms and repeat that block for a large enough number of times, then in the limit in which the number of steps becomes infinitely large and the time evolutions become infinitesimally small, this actually becomes an equality. Okay, so this immediately suggests an algorithm. And the algorithm is basically, we would just take each of the terms that appear in the Hamiltonian, exponentiate them, and then simply do those exponentials in succession for some small time segments. And then that gives us one whole block. And then we simply repeat that block a large number of times, right? Now, of course, this incurs some approximation error. And the approximation error, if you do things in this way, for one small time step, delta t, in the limit in which delta t goes to 0, is approximately the order delta t squared. Okay. So now let's do some counting for how much, what the cost of this approach would be, right? So we said that, like, okay, we want to approximate e to the minus iht. We said we're going to break it up into some small time evolutions, e to the minus ih delta t, and then we're going to repeat it for n steps, right? So we have, the total cost is going to be n times some number, right? And that number is, in each block, we have m many exponentials, right? And each of those exponentials have some cost by themselves as well of implementation. So let me just call that cost C sub h, right? So then the total cost is the number of steps times the number of exponentials in each step times the cost of implementing any one of those exponentials, right? So nm times C sub h. Okay, good. So now what I say is that, okay, I want the overall target accuracy of my entire algorithm to be epsilon. Okay, so now what this expression is telling me is that the approximation error of one time segment is order delta t squared. So the approximation of error of n time segments is going to be n times delta t squared, right? Which is t squared over n. So if I want t squared over n to be epsilon, then n is t squared over epsilon. And so that's why I get this kind of counting where the total cost is going to scale as, quadratically in t, linearly in the total number of terms, and one over the approximation, the target approximation. Okay. So one thing I want to stress immediately is that you can sort of immediately see that this approach, of course, won't work for exponentially long times, right? And it certainly won't work if the number of terms in the Hamiltonian is exponential in the number of qubits or the size of the problem, right? And so typically these are constraints that are very natural, right? So, and in fact, for the dependence on the time, there is this theorem called the no fast forwarding theorem, which says that you can actually do better than linear scaling in t. So while certain quantum mechanical systems can be fast forwardable, for completely generic systems, you cannot, on average, do better, than the system actually simulating itself in some sense, right? Because the system simulates itself in time t, and you need almost about as much dependence, about as much time in your simulation as well. And the number of terms over here, let me also just stress that when you encode a Hamiltonian into qubit operators, so recall that the poly operators form a basis for operators in CN, right? And so one very naive way to encode it is to basically take whatever operator you have, whatever matrix you have, and express it as a sum of 4 to the n poly operators. That's a very bad way to do it because now you have an exponential number of terms and m is now exponential, and that's going to kill whatever possible quantum advantage you could get. Yeah.
Can I ask a question for the no cost? Like, it seems that if I'm simulating a quantum spin mass or something which has a very rugged landscape, then the natural dynamics take exponentially long, but I could probably do it linearly.
Well, okay, so if I understood the question, you're saying that, I mean, some systems such as the spin glass, like, I mean, they could take an exponential amount of time to simulate it. I mean, to simulate themselves, and can I fast forward such? So there are Hamiltonians, which you can certainly fast forward. And, you know, I'm not familiar with the particular example maybe that you're referring to, but it could be the case that it's fast forwardable. But completely generically, the statement is that you know, you need roughly the same amount of time as a system would need to in order to simulate itself. So if somehow you got the Hamiltonian of the universe, you can't carry out a simulation of the universe faster than the universe actually evolves itself. You know, that's one way to maybe think about it. Okay, but so you know, I just wanted to stress that M should be something that's like, you know, scales polynomially in the size of the problem input. Typically that's something that's like often guaranteed by the encodings, like the Jordan-Wigner transformation and so forth. Like, you know, this thing is something that's often preserved, but I just wanted to mention it. So now I also want to convince you that the C sub h, the cost of actually implementing any one exponential, this is also quite efficient. So let's take a look at how we're actually going to implement each one of these exponentials, right? And I'll start off with a very simple example. The example of the term ZZ, right? So remember that the computational basis is actually the basis in which the Pauli operator Z is diagonal, right? So 0 is the +1 eigenstate of Z and 1 is the -1 eigenstate of Z. So ZZ acting on these computational basis states simply produces these particular phases on those states, right? And so what that means is e to the -I theta ZZ produces these particular phases, right? And now if you recall the RZ gate, which is a rotation of you know, theta about the Z-axis, in the computational basis, again, of course, it's diagonal, and it has this effect on, you know, this is the representation it has in the computational basis. So my claim now is that in order to realize e to the -I theta ZZ, I can simply run this particular circuit. So let's see why this works, right? Let's say that Q0 is the leftmost qubit over here and Q1 is the rightmost qubit, right? So now I do a C naught operation. What that means is that I completely leave these first two basis states unchanged, right? And these last two basis states, I'm going to change 1, 0 to a 1, 1 and 1, 1 to a 1, 0. And now I apply RZ2 theta. So what that means is that it's going to give an e to the -I theta phase to wherever I see a 0, which is going to be here and here, because remember I've applied the C naught. And so that gives you know, precisely the phase that I'm looking for. And it's going to give a phase of e to the +I theta to the 1 state, which is going to be here and here, because again, I've applied a C naught. And so that's again precisely the phase that I get. And once I get the right phase, then I simply have to undo the operation that I just did, right? So I have to run the dagger of whatever this operation was. And C naught is its own inverse, and so, you know, I just apply it again, and I'm back to the original basis states. Okay, good. So now let's see how this works in kind of more generality, right? So if I have not just two Z's, but I had K Z's, then maybe this is you know, one way of looking at it. So the product of K many Z's on K many qubits basically goes as -1 to the exclusive OR of all those particular bits. Exclusive OR is a classical operation which basically just says it's 1 if both the bits disagree with one another, and it's 0 if they're equal to one another. Okay, and so what that says is e to the -I theta product of those Z's is precisely you know, this particular phase, which again depends on the exclusive OR. But now notice that RZ of 2 theta acting on 1 qubit, which somehow stores the exclusive OR of all those particular bits, also produces exactly the phase that I'm looking for. Okay, so I need one more observation to sort of write down a completely general circuit for how to compile this kind of operation. So I note that the C naught operation also produces the XOR operation, but this time it does so on the bit values themselves, not in the phases. Okay, so what that means is that control, if I say that the control qubit is I and the target qubit is J, then control on this value, it's going to change the value of B sub J to the exclusive OR of B sub I and B sub J. And I just mentioned that the C0 operation is its own inverse, right? So in other words, if I apply the C0 operation to this thing, I better get back the same state that I started off with, which I do. And another way of looking at it is that the exclusive OR operation of any bit with itself is again 0, right? And so what that means is if I apply C0 to these two qubits, I will get BI XOR BI XOR BJ, and since BI XOR BI is 0, I'll just get BJ again. Okay, so now this tells us exactly how we need to implement e to the I theta Z1 through ZK. We will, first of all, produce a C0 ladder, right? So we're going to start off with this register B1 through BK, and then we're going to apply a sequence of C0s such that it changes B2 to B1 plus B2 or B1 XOR B2, and then it changes B3 to B1 plus B2 plus B3, and so on and so forth until I've stored the XOR values of all those particular bits in the very last qubit. And now that I have the value of the XOR in the very last qubit, I will simply apply an RZ gate and extract the phase that I need. Okay, and once I've extracted that phase, I simply need to undo the operation that I performed in order to get to this point. And that just basically means running this particular part of the circuit in reverse. And remember, when I say reverse, C0 is its own dagger, so it doesn't matter. But reverse basically means run the operations in the reverse order and also take their daggers, right? So if they were unitary, they had phases, we would need to be careful about that too. So in circuit form, it looks kind of like this, right? So I basically have the initial C0 ladder. I do an RZ2 theta on the final qubit, and then I basically just undo the operation. Okay. And so notice that this is actually quite efficient, right? So because if I have k many qubits, then I need like 2 times k minus 1 C0s and a single qubit operation, and that's it. So this is like order k. Okay, so that takes care of e to the minus I theta ZZ. Or Z1 through ZK. How do we do this for general Pauli operators? Well, it's a very small step from here. Basically, we just note that you can apply single qubit operations to diagonalize any Pauli operator and put it in the Z basis. So, for example, X is related. X can be diagonalized using the Hadamard operator. Or the Hadamard gate, and Y can be diagonalized using the Hadamard as well as this S gate, which is produces a phase of I on the one state. Okay, so as an example, if I wanted to exponentiate x1 y2 z3, I would simply sandwich e to the I theta z1 z2 z3 on both sides by the change of basis gates that I need. Okay. And so, this now completes our prescription of how to compile e to the minus I theta Pauli operators, right? Like we would basically just need, like I said, order k C0s plus order k single qubit gates. And so that brings, the total cost of CH to be order k. Yes?
Is you just have to observe the Hamiltonian figure out how you compose it, or is there some prescription how you can generate those values?
So is the question, is there a general prescription for how to break down the Hamiltonian into particular Pauli operators? So, okay, so that kind of goes back to the original question of how do we actually encode the Hamiltonian into Pauli operators? And there's a wide variety of choices. There's no one particular good choice. Even I mentioned the Jordan-Wigner transformation, but there's been a lot of work on actually how to map fermions onto qubits. Like Jordan-Wigner is maybe historically the earliest one, but you also have like this Pravy-Kitaev encoding, and then there's like, I think people call it the parity encoding. And there's been a lot of work in like encoding, field theories onto qubit registers themselves. So there's no unique answer per se. But what I wanted to convince you over here is that no matter what Pauli operator you have, if you just wanted to exponentiate that Pauli operator, it's just the cost is just going to scale as the locality of that operator. Okay. Yes.
I guess if you change the order of the HI, that when it looks like if you put 13 HI together with you kind of give way to
Okay. So the question was about, if I understood it correctly, does the ordering of these exponentials have any particular effect, and are there clever ways to order them? Okay, good. So I mean, it may be the case that some subset of these exponentials actually commute with one another, right? And if that's the case, then you would want to do those in one block. Right. So in other words, like, I mean, if H1 and HM commute, then I would personally want to do H1 and HM, commuted together. And the reason sort of goes back to the BCH formula, because the exponential of H1 plus HM is going to exactly equal the exponential of H1 times the exponential of HM. Whereas if you put it in between, then you might incur some additional errors. Does that make sense?
Pairwise, but not all of them.
There's a whole wide variety of techniques of like various trade-offs. Like, I mean, some people like to like greedily collect them together. It can really depend. But this is kind of like the art and science of, I guess, like these trauterization-based methods. But I mean, that's a great question, and I certainly encourage you, to think a bit more about it. But yes, I mean, like there are various strategies, I guess, to like, improve, the sort of costs that I'm giving you right now. Of course, none of what I said changes anything about the asymptotic cost of this. Like, the cost is still going to be delta t squared, order delta t squared, right? But these little bits of changes and clever techniques can sort of like, improve estimates as well. Let me just complete the loop on trauterization by saying that Suzuki actually discovered these higher order formulas where instead of like just a simple-minded product of exponentials, you can also have like these other combinations of exponentials, right? So over here, if you look a bit closer, you'll notice that I am actually evolving not by delta t, but rather by delta t over 2, all the way up to the first n-1 terms. And I'm then evolving according to delta t, and then again, according to delta t over 2 in the reverse order. So it's a funny looking expression, but then Suzuki was able to show that if you compose your exponentials in this way, then the error for some small time segment is actually order delta t cubed instead of order delta t squared as before. And in fact, there's even higher order, exponentials or higher order formulas, with their own sort of like weird combinations of exponentials, which increasingly give better and better approximations. Okay, and they satisfy this kind of, they're defined through this kind of recursive relationship. So it's, for some integer k, basically, if you take the exponential, the product of exponentials defined by s at 2k, then the error per time step, or sorry, per segment, per time step, is order delta t raised to the power 2k plus 1. Okay, and that actually explains why I have Suzuki in the Suzuki-Lee-Schroeder formula, even though people just, they'll call it Suzuki Trotter or trauterization for short. They all roughly mean the same things. And so now if we do everything, like if we do all the analysis and everything, like, I'm going to forget about like dependencies on M and so forth, because I wanted to talk about it at the beginning just to impress upon you that the number of terms needs to be, a reasonable amount. But basically, you'll find that from a computer science perspective, what people mostly care about is how the cost of the simulation scales as typically T and epsilon, and maybe on, what the coefficients of the Hamiltonian are as well. And so one funny thing about these Suzuki-Trotter-based methods is that the cost actually depends on the coefficients through their commutators. And this is going to be a different kind of dependence than we'll see, in some of the upcoming methods. So I'll talk about the linear combination of unitaries method next, but before I do that, let me see if there are any other questions about Trotterization. Yes. You just have more. Oh, so what is the downside of using these particular types of weirder exponentials? It's just sort of like a longer circuit depth, right? So like you can immediately see that this is like many more exponentials. Like earlier I had like m, now there are more, and it's not. Oftentimes, like, you have to do sort of like a numerical kind of analysis to like actually see like if you're actually winning something, by doing those longer exponentials or not, like if the increase in error is actually that much better or not, these kinds of considerations especially become all the more important when you have limited fidelities and so forth, So, I mean, I think that maybe beyond like the second order, or sorry, like I guess the third order or so, like I've personally not really seen too much, efforts. Yeah, sorry.
The thing you mentioned a bit before, can that be thought of as taking the cube of infinity and you get the linear exponential in time? Like on the next.
You mean over here?
Yeah.
So the question is, if you take the k going to infinity limit, then sorry, I didn't catch the next part of the question. That's right. That's right. Yes. Yes. So in that limit, you would get the linear, scaling in time that you would. Yes. And you're also taking some crazy square root of epsilon, in the denominator. Okay. So let me now talk about the linear combination of unitaries method. So in the Trotterization technique, we were approximating e to the minus iht as a product of unitaries, but it's also quite natural to think of e to the minus iht as a sum of unitaries, right? And so here again, the idea is that I'm going to break up the overall time evolution into a bunch of small time evolutions, t over r, and then I would repeat that for some, number of segments r. But now, each of those individual segments, I'm going to express as a Taylor series expansion, and then truncate that Taylor series to some order capital K, right? And then the idea is that this, whatever truncation I perform, that's going to control the approximation error of any one particular time step. And I want that approximation error to be roughly epsilon over r, so that the total approximation error of r steps is going to be epsilon, my target approximation. Okay. So good. So now then the problem becomes that for each of those time segments, we want to implement this linear combination of unitaries. Remember now that we're working with Pauli operators, right? So that this H now is a sum of Pauli operators. And then if I rearrange things, sufficiently, I will be able to write this entire sum as some coefficients times Paulis, and Paulis are both Hermitian and unitary. Yes, question. Oh, that's interesting. So the question is, the two methods, this method and the previous one, have analogs with path integral and stochastic Monte Carlo. Yeah, I mean, I suppose that might be a fair way of looking at it. Yeah. I mean, I guess the only difference it really makes from a quantum computing perspective is like, how do you actually implement these things on a digital quantum computing device? But that's a useful, I mean, that's a nice analogy to think about. Okay, so now in order to actually implement this combination of unitaries on a quantum computer, we immediately run into a problem, right? Because the sum of unitaries is not in general a unitary operation. And quantum computers can only really apply unitary operations, right? So as a very simple example, I mean, if I take the sum of the unitaries identity and z, then this produces just like the projection operator on the zero state, which is very non-unitary, right? So the solution, as you have sort of seen in some other talks by now as well, is that we can block encode that non-unitary operation in a larger unitary, right? So the idea is that we can initiate some ancillary qubit in the zero state, and then now we have, this larger Hilbert space such that it encodes the state psi on the top part of this state. And now basically we're just interested in this operation v tilde acting on psi, and the dots represent stuff that we don't really care about. Okay, so we use ancillas to get around this problem. Okay, so the prescription for LCU basically becomes that if we have some linear sum of these unitaries, and we're going to assume that all the alpha i's are real and positive, which means that we're basically absorbed any phases into the definitions of the UIs, okay? So the prescription then becomes to be able to construct these following two unitaries. So the first unitary, which is often called the prepare circuit, basically prepares a superposition of states with the amplitudes given by the coefficients appearing in the linear combination of unitaries, okay? And of course, it has to be a normalized superposition and all that. And then the so-called select circuit, which conditioned on the value of these states being in some particular basis state I, applies the unitary U sub I onto the actual state of interest, okay? And together, we can use these to realize the linear combination of unitaries that, we can use that to realize the operation A on the state of interest. And so it looks something like this. We have an ancillary register on which we apply the U prep circuit. Once we apply that, we've produced this superposition of the amplitudes, which are given by the coefficients that appear in the sum of unitaries. But right now, the two registers are still unentangled, right? The U select operation actually entangles those two operations together, right? So now, basically, if we start off from here, remember that U select conditions itself on the state of the first register being in the I state, and conditioned on that, it applies the unitary U sub I. So now we have an entangled state like this. And finally, that last part undoes the operation of U prep. So this part is actually a little bit tricky because U prep dagger, I only really just defined the action of U prep on the zero state. I don't know what it does to any of the other I's, right? But nevertheless, you can show that, if you compute it out, then basically you can show that the coefficient of the ancilla being in the zero state looks something like, gives you precisely the operation that you want. So remember that A is the linear sum of the unitaries. And the other state, because I don't exactly know what the action was, but I don't need to know. It's just stuff I don't care about. The only thing I need to know about it is that this state is orthogonal to whatever this is, because if I apply the projector of the ancilla being in the zero state to that state, then it just projects it to the zero state. Okay. And the success probability. So now, you could in principle just stop here and say like, okay, if all I wanted was just this linear sum with some probability, I could just run this circuit and be done. And I will just repeat it for order roughly alpha squared over a psi squared many times until I sample the entire ancillary register being in the zero state. So that's the method of like post-selection, which you might have heard about in earlier lectures, right? We simply measure out the ancillary register, and with some particular probability, we'll get that the entire register reads out to be in the all zero state. When that happens, we know that the state that we produced in this particular register is precisely A times psi. Okay. But we want to get rid of post-selection. So can we do something about it? So here we'll apply this technique of robust oblivious amplitude amplification, which is a generalization of amplitude amplification, which itself you could think of as a generalization of Grover's famous algorithm for unstructured search, right? And Grover's algorithm, just to give you like a 30-second version, it basically goes as you start off with some initial state, which has some non-zero overlap with some, bit string that you want to find, right? You have access to an oracle that will tell you, that will give a phase of -1 to, the chosen bit string and +1 to the other one. So it's basically a reflection operator. And so Grover's algorithm is basically a sequence of reflections about the chosen bit string and the initial state. And if you do those enough number of times, you have amplified the amplitude of the chosen bit string. So here we're doing something similar like that, except that the reflection operator, it only needs to reflect about the ancillary register being in the zero state, okay? And moreover, we're basically going to assume that we have some unitary W that acts on this entire register of qubits, and it produces some possibly non-unitary operation V tilde, and it produces, this state phi perp, which, as before, I mean, this is orthogonal to this particular state. And if we can satisfy these two conditions, namely this S over here is epsilon close to 2, and this V tilde in, say, the spectral norm is epsilon close to some unitary V, then basically if we compose this particular unitary, then the action of that entire unitary is epsilon close to the identity times the unitary V acting on the system, psi. Okay, so what this buys you is that now you have totally gotten rid of the post-selection, technique. Like you could just apply this unitary instead, and it will give you to order epsilon, the unitary you need. Yes, question. Oh, reflection basically, well, okay. So let's just maybe like look at what this does, right? So, so the question was, what is a reflection operator, right? So reflections are typically something like 2 times a projector minus the identity, right? So let's think about like if the projector was just on some bit string, right? So what that means is that if I apply this thing to now a bit string, I will get the bit string back itself. And if I apply this operation to something that is orthogonal to that bit string, I will get minus that thing. So this is kind of like a reflection about that bit string because it leaves that bit string alone, but it sends whatever is orthogonal to it to minus itself. So that's why we call it like a reflection about this particular axis. Okay. So the reflection operator, let me just quickly note. So, this A unitary is composed of W's and R's, and W is, composed of the circuit that we just saw. And we'll go into a little bit more detail of like how you actually implement this. But this reflection operator is also something that I can implement rather straightforwardly, right? So basically now, I want to implement this reflection operator about the ancillary register being in the all zero state. And let's say that this was like, composed of like n qubits, right? So then I can use this technique of phase kickback, which basically says like, okay, if I simply control, if I apply a condition, if I apply a conditional NOT gate, where the condition is that all those qubits are going to be in the zero state. So this open circle, typically when you see C-NOT gates, you see like a black dot with a target operation. When you see a white dot like this or an open circle, that means that you're controlling on the value of that qubit being in the zero state, okay? So now what we're doing is we're saying that the value of all those qubits are going to be in the zero state, okay? And this can be related to the C-NOT or like, the usual black dots by simply putting X gates on either side, right? Because X times 0 is 1. Okay, so the main idea behind phase kickback is that you can use this ancillary qubit to obtain a phase that is basically shared by both those registers, right? It's not like I can, this phase is uniquely assigned to the minus state or this state, like it's shared between the entire register, right? But I can do this operation in such a way that I can still sort of, at the end of this operation, this part of the register is still sort of like unentangled with this part of the register. So I can really just think of, this part of the register just being like producing the phases that are required on the original part of the register. And the way it works is like, conditioned on all these qubits being in the 0 state, if I apply just the NOT operation, which is, just an X gate, right? Then you can see that this minus state, the effect it has on this is basically just to send it to -1 times this state, right? Because 0 gets sent to a 1 and 1 gets sent to a 0. And this state, by the way, is very simple to prepare as well. You just have to apply a Hadamard gate followed by a Z gate, or you can apply an X gate followed by a Hadamard gate to the 0 state, okay? All right, so now let's return to the problem at hand, which is basically we want to approximate a single step in the LCU method. By truncating it to by truncating the Taylor series to some, yes, question. Sorry?
About the amplification step, the amplitude amplification step, aren't you still applying W multiple times? So wouldn't that be good? Are we actually saving on applications of W?
Then okay, so the question was, instead of oblivious amplitude amplification, could you not just apply W over and over again, right? So W produces, I guess if we go back here.
Sorry, not applying W multiple times to the same state. I'd say post-selection would involve applying W to multiple states and selection from. What are we actually saving from applications of W?
Well, if you do things, so if you apply W and then post-select, even if okay, so for one, if you apply W many, many times, right, then the post-selection probability, like of that answer, it's just going to be a product of those probabilities, right? Roughly. I think that works out. But if, if you're going to post-select and then apply W again, well, for one thing, if you post-select, then you're basically done. Then you've realized that operation anyways, and you don't need to apply W again. So if you're okay with doing that, if somehow, the probabilities work out in such a way, let's maybe go to where we did talk about, oh yeah, it was right here. Yeah, so this A side, so the thing that generically messes this up, by the way, if you specify the problem Hamiltonian, then I know what alpha, the norm of alpha is, right? It's just the sum of all the alphas squared. The thing that's sort of tricky is what the state psi is and what that operator A is. And in general, that can be very, it can depend from problem to problem. So it could turn out that this is actually quite a reasonable number. And if it is, then, if the probability of getting a heads is P, then you just flip the coin P many times on average before you get a heads, right? And if that P is sufficiently sufficiently large, then maybe you're fine with doing that. And oftentimes in practice, especially in the NIST era, people will rely on post-selection kind of techniques as well. So, that's a perfectly valid approach. But I just wanted to mention that, if this is a problem, then you certainly can get around it by using robust oblivious amplitude amplification. Any other questions at this stage? Okay. Okay, so now we said that we want the approximation error of any single segment to be roughly epsilon over R. And this is ensured by taking the truncation in the Taylor series to be roughly log T over epsilon over log T over epsilon. where this t now, capital T, is the sum of coefficients times the time evolution of time, t, okay? And, you know, it's a nice result that, like, if you choose k in this manner, then the approximation error is going to be epsilon over r, okay? Okay, so that was one condition for oblivious amplitude amplification, is that, you know, we need whatever operation that we want, you know, this is going to be like, you know, like some approximation error close to like some unitary. And also we want the sum of those coefficients s to be epsilon over r close to 2. And that can be satisfied by choosing the number of segments r to be roughly order t, order capital T. Okay. So now this gives us the prescription for what our UPrep circuit should be. So UPrep needs to basically prepare all these, the coefficients that appear in the unitaries, in the linear sum of unitaries, as amplitudes of some superposition of basis states. Okay, and now our basis states, because we're doing this kind of Taylor series expansion, our basis states are a little bit funny, right? It's like they're composed of two different things. They're composed of this register, which I'm going to call the K register, which tells me what you know, what power of the in the power series I am in, right? So this K runs from values from 0 to the highest Taylor expansion order, K. And each one of these registers, L1 through Lk, they run from values 1 through L, where L is the total number of terms that appears in the Hamiltonian. Okay. And now we have these particular coefficients as well. Like, I mean, so these coefficients come from the Taylor series expansion, and these coefficients, these alphas, these come from the actual, you know, sum of unitaries that was the Hamiltonian itself. Okay. So now this UPrep needs to do both these things, right? Like, it needs to prepare this weird kind of superposition, which involves both the K register as well as these L registers. And notice that for now, I'm basically truncating this register to small k, where small k actually goes from 0 through big K. That's not actually how we're going to implement it, but I just want to make you know, a midway jump from the actual Taylor series expansion to something that I can sort of put on a quantum computer. But first, let's deal with how we can actually prepare the K part of the register. And we're going to use two different types of encodings for the L registers and the K registers. The K registers are going to be encoded using this kind of unary encoding, where the first K qubits are going to be in the 1 state, and the remaining capital K minus K qubits are just going to be in the 0 state. Okay. And basically, what I'm going to prepare is a state that looks as follows. So it has like these particular amplitudes, and these are the particular basis elements. Okay. And the way to do it is hopefully I could illustrate it with just a very concrete example. For example, if I have K equals 3, and I start off with the all 0 state, and let me just think of the leftmost qubit as being qubit 0. And now if I just apply an Ry rotation to this qubit 0 by some angle theta naught, I will just produce this particular superposition, right? It only mixes the 0 and the 1 states of the leftmost qubit. Now, if I apply a controlled rotation operator controlled on the value of the 0th qubit, which is the leftmost qubit, I apply a rotation Ry on the first qubit, which is this middle qubit. It does nothing to this basis element because the qubit over here is in the 0 state, right? But it does mix the 0 and the 1 state of the middle qubit. And so I produce these particular amplitudes. And so you can see where I'm going with this, right? I can continue on in this fashion. I can control on the value of the first qubit being in the 1 state, and then apply an Ry rotation on the second qubit. And now I've basically mixed the 110 state with the 111 state, right? And so you can see that I'm producing precisely states of the form that look like this. But now I have to just match what these amplitudes are to these particular numbers, right? And a completely general amplitude depends, of course, on several angles. But the nice thing, the reason why this works is because I can now, first of all, fix that very first amplitude, right? So in complete generality, it would look something like this, right? And so the idea is that I can fix what that very first angle theta naught is by simply matching whatever cos theta naught over 2 has to equal, this normalization factor. And then, one step down, I'll have something like sine theta naught over 2 times cos theta 1 over 2. And that's going to equal T over R square root over the normalization factor. And so the idea is that, you solve for in for any one k, like you have a bunch of products of sines of angles which you have solved for in the previous steps, and then you use that particular step to solve for theta sub k, using just like whatever this cosine expression is. Okay. So this you can of course do classically, and then figure out what the rotation angles are, and then just apply the circuit. And so this circuit, as we've just seen, I mean, it's just going to use order capital K many gates, right? Because you just do like a bunch of control rotations on the K qubits. Okay, so that takes care of the first part of the UPrep circuit. So we have like about half an hour left, is that right? Okay, all right. Okay, so that takes care of the first part of UPrep. The second part is I also need to do something about these alphas, right? And this register, this series of registers Ls1 through Lk. So now what I'm actually going to do is, instead of like having small k many registers, I'm actually going to expand it to capital K many registers. And what I'm going to say is that on each one of those registers, I'm going to use a binary encoding, right? So if I have L many terms, I'm going to use log L many qubits, which is a different type of encoding that I use for the K register, right? Because there I had K many values and I used K many qubits, right? But here I'm using log L many qubits. And I will have K such registers. So in all, I will have K times log L many ancillary qubits. And in each one of those registers, I'm going to prepare basically this kind of superposition. Now we're going to see that basically this will require that each one of these is going to require L times log L many gates to prepare. And because I need to do this K many times, the overall cost is going to be like K times L times log L. Okay. So the way that it works roughly is as follows. It's kind of like this general method that is often referred to as uniformly controlled rolls. In circuit form, it looks kind of like this, where the amplitudes, alphas, are real. I've sort of overloaded notation over here. So these alpha i's are now assumed to be, to some absolute square to 1, which are slightly different from the alphas of the previous slide. But basically, if you have some state psi with some real amplitudes that are given by those alphas, then you can figure out via this formula what those rotation angles have to be. And the intuition is very much along the lines of what I just described earlier to prepare the K part of the register, which is that basically you apply an initial rotation of some, the leftmost qubit or whatever. And now the only difference now is that, earlier we were preparing states that look like 0, 0, 0, 1, 0, 0, 1, 1, 0, etc. Now we have to prepare superposition of all the bit strings. So instead of only controlling on the value of the qubit being in the 1 state, we also have to control the value of the qubit being in the 0 state, and then apply another corresponding operation. Okay. And in general, whenever we apply in our Y rotation on some qubit, K, we actually apply different rotations conditioned on all the previous qubits being in some particular bit string. So this actually, of course, as you can see, scales exponentially in, the number of qubits, but that's fine because, L over here, like L is actually the thing that we actually care about, right? So it's fine if, it's exponential in the number of qubits, because we don't care about you know, cost as the scaling of the qubits here. We care about the cost as a function of the scaling in L, right? So, okay, good. So now we need L many of these steps to basically, like, I mean, you know, like the cost scales roughly as exponential in the number of qubits, which basically means that, you know, it scales as roughly as L. That's how many gates you need to apply. But each of these gates in turn, you know, it's basically a multi-controlled operation, right? And it can be shown that if you have, like, say, a multi-controlled NOT gate, something like C to the N naught, right? Then that operation could be implemented using order N primitive operations. Okay, and since order N over here is actually log L, that's why the cost is something like L times log L. Okay. So good. So now that basically completes our definition of the prepare step. And let me just say that, like, I mean, you know, it's a very small, perhaps barely noticeable change, but in the previous slides, I had this set of registers being truncated at small k to make it much more directly analogous to the power series expansion. But here, like, the method that I just described actually uses all big K registers. And that's totally fine as long as I'm careful about how I define my select circuit, okay? And so that brings us to this next step of the select step. So previously, I had talked about, you know, in full generality, the select part of LCU basically conditions itself on, you know, the ancillary register being in some state L, where these values run from, you know, well, 0 through L minus 1, L being the number of terms in the Hamiltonian sum, and UL being the actual terms in the Hamiltonian sum. But for the particular kind of, you know, encoding that we've chosen to implement this Taylor series approximation, well, this L register is actually composed of, like, this K register as well as all these L registers, right? So the select operation that we actually want to implement looks something like this. So conditioned on the K register, and you know, these values of the first K L registers, we want to apply precisely this particular unitary. And now this operator in turn can be implemented via a series of operations that look like follows. So this B sub j encodes the bit value of the jth qubit in the K register. Okay, so remember the K register was encoded using this kind of unary encoding, where we have like 0, 0, 0, 1, 0, 0, and so forth, right? And so this basically tells us, like, you know, what power in the power series expansion we're currently in. Okay, and dependent on that, I will simply pick out the part of the register that corresponds to that part of the Taylor series expansion. Okay, so if it's like, you know, K equals 2, then I would pick like the L equals 2, L2 register over here. But remember that L2 actually spans all the values from 0 to L. So I have to do this for like all the values of L in that particular register as well. So somewhat schematically, it looks like this, right? So for example, if I truncate the Taylor series to order K equals 3, and I have a Hamiltonian that's only a superposition, that's only a sum of 2 terms, L equals 2, then I only need a single qubit, because it's, you know, a single qubit is enough to capture two sums, right, 2 states. But I need K many copies of those L registers. So I have like 3 L1, L2, and L3 registers, right? And because K is 3, I actually need K many qubits to, you know, to have this part of the register. And now basically the idea is that, you know, controlled on that, you know, the first value of K, and you know, running through all the possible L's, I will implement the particular unitaries that appear in the LCU. Okay. And so this entire operation basically realizes what that uSelect operation is. And so let me just mention that here too, I mean, you know, if we do the counting, We have to do k many of these, conditional gates, but in each segment of the k, we again have to do L times, we have to run through L many values of these unitaries, right? So this gives us the count in k times L. Because we have to do, right now we have a very simple example in which this is just a single qubit. But in general, if we have L many terms, then we need to control on the state of log L many qubits. And as I just mentioned, if you have a C to the log L naught, then this can be implemented using order log L many primitive operations, right? And so that's why we have this log L factor. And now finally, this U naught, these UIs themselves could be some M local Pauli operators, right? And in which case, then, the cost of actually implementing that also then gives us a prefactor of M. I'm going to suppress that for in later slides, but I just wanted to mention that the locality also sort of makes its appearance in this matter. Okay. So altogether, if you write it out and work it out carefully, it looks something like this. Where now the nice thing about it is that even though I have like a full k's worth of registers, I can actually mimic very closely the Taylor series expansion because at any level of the expansion, whether it's the 0th expansion or 1 or 2, I'm basically entangling just as many registers, the L registers, as I need in order to realize these unitaries. And these unitaries are also, moreover, precisely the unitaries that appear in the original Hamiltonian sum. It's not like when I do h squared, I have to recalculate, for example, if Hamiltonian was like xx plus yy, and I were to square it, I don't need to calculate what xx times yy and all those factors are. I just need to know what this sum is once and for all. And using this kind of select operations and uprep operations, I could just deal with arbitrary Taylor series, arbitrary Taylor series orders. Okay. So if I put everything together, we just saw that the cost of a single segment is roughly KL log L. And if you recall, K, which is the truncation order, that was log T over epsilon over log T over epsilon. So the total cost of one segment looks something like this. And the total number of segments is R, which if you recall was order capital T. And so the total cost scales as, this expression at the bottom. So one thing I will like to point out is that the way that this differs from the trotterization technique is that, well, one, the dependence on the coefficients now appears as a linear sum rather than information about, about the commutation properties between the individual operators. It's still linear in T, but now the dependence on epsilon is much, much better than 1 over epsilon. Okay, so in asymptotic complexity terms, this is a much better algorithm to implement than using the trotterization method. So even though trotterization is conceptually so much simpler, we had to go through a lot of song and dance to get to this particular expression, right? But in asymptotic complexity terms, we also do a lot better. Okay. Any questions about LCU before we briefly touch on the very final topic?
Yeah, I was wondering, in practice, what is the key that you're using to maybe be competitive with first order computation?
What is the, I'm sorry, I didn't get.
Which key are you choosing in practice if you want to be competitive against trotterization with first order?
Oh, so K, I mean, okay, so K, that it has to be log T over epsilon over log T over epsilon, but that's only in order terms, right? And order basically means that you need to choose what the prefactor is. And that prefactor is something that you sort of have to choose, test out numerically. Yeah. But in sort of scaling terms, K is really chosen. Maybe, if I go back to where K was sort of defined explicitly. Yeah, so K scales like this in, what the time is, what the sum of the coefficients are, and what the target approximation epsilon is, okay? Now, of course, this big O notation, it sort of hides whatever prefactor might appear over here. But you can sort of like convince yourself if you do simple enough kind of exercises that, like for baby toy examples, like it could be like the prefactor is just a 10 or something. I mean, that's something that you have to play around with. But the sort of dependence on the fundamental parameters of the problem, it looks like this. Okay. Any other question? Okay. So now I will like to briefly mention the quantum singular value transform method, which is actually a pretty recent sort of development. But I would like to mention it nevertheless. So there's this remarkable kind of theorem which goes by the name of quantum signal processing, and which Giacomo also talked about yesterday a little bit, that if you want to produce, so for any polynomials P of A and Q of A, which satisfy these, fairly reasonable constraints. So the degree of P has to be some, some degree, some number D, and it has to be like an even function if D is even, or an odd function if D is odd. And A, the parameter in which it's a polynomial in, is some value between -1 and 1. Then actually you can write the sequence of single qubit operations, these Z rotations, interleaved with this W rotations, which is the function of A. And this really you could think of as an X rotation as well. Then you can basically recover what those polynomials are. Okay. So you could think of this as just kind of an observation. But the remarkable thing about this is that it isn't just true for these kind of like single qubit scenarios. We also have this theorem, which I guess you could call the quantum eigenvalue transform, which says that if you're given a block encoding of some Hamiltonian inside a unitary operation, which looks like this, and if you're given access to a conditional phase shift operation, so this is basically like the exponential of some reflection operator, right? Then basically now you can again compose a sequence of unitaries such that that unitary now realizes a block encoding of some polynomial function of that Hamiltonian. And so functions of operators are in general defined. I mean, one way to think of it is like it's a function of the eigenvalues of that operator, right? Written in the basis in which that operator is diagonal, right? So this is why, I mean, we call it like the eigenvalue transformation, because it's transforming the eigenvalues. And really the only conditions that this polynomial function is subject to are basically the conditions on P of the previous theorem, namely that it has degree D and that it has a definite parity D mod 2. Okay. And if D is even, then you would compose this particular sequence of unitaries, and if D is odd, then you would do this particular sequence of unitaries. So as a very explicit example of a block encoding of a Hamiltonian, you could consider this particular case, right? Like where now I've actually, I'm just using a single ancillary qubit to block encode H, right? And you could think of it as like, basically Z product H plus X product 1 minus H squared, and 1 minus H squared square root, again, you could think of as, a sum of 1 minus lambda squared square root times projector on lambda. And its action on these basis states, where 0 and 1 are the basis states of the ancillary qubit, and lambda are the eigenstates of this Hamiltonian. So if the second register is in the state that diagonalizes the Hamiltonian, then basically this is the action of that U, right? And so in that basis, you can sort of work out that this U can actually be written as a direct sum of these rotation operators, which look like this and are dependent. We have one such rotation operator for each eigenvalue of the Hamiltonian. And so we say that the Hamiltonian has been qubitized, okay? And this terminology actually, I mean, still lingers even when we're not using just a single qubit to block encode the Hamiltonian. And in the remaining time, I'll just mention, one other sort of explicit way to block encode the Hamiltonian and actually do things with it. But somehow the term qubitization seems to have stuck around. So when people talk about qubitization, they may actually be referring to this QSVT kind of approach as well. At least this is a sociological thing that I've been discovering myself. Okay, so we talked about the LCU method and using the UPrep and the USelect circuits and so forth. And the cool thing is that you can actually use those unitaries to actually create a block encoding of H, right? Because now notice that, and so of course, when H belongs as a block in some unitary, then you have to make sure that its operator norm is bounded by 1. And so you have to divide it out by this particular norm. And now this particular thing, I mean, you can write it out as U being sandwiched, branchetted by G, where G is precisely the state given to you by the UPrep circuit. And U is precisely the USelect circuit. Okay, so it's a nice exercise for you to carry out. Like if you just compute, if you just calculate what this inner product is, I guess, or or this expectation value is of the unitary U, then you'll basically get H. Right. It's not an expectation value because I guess that implies a number, but it's just bracketing out one part of the register to get an operator on the remaining part of the qubits. Okay. So that basically tells you, what U has to be. Remember that in order to apply the QSVT, we need to know what U is and we need to know what pi is. So pi, I'll tell you how you can implement it. Again, here the idea is that, so pi sub phi is defined as the exponential of the reflection operator built out of the projector onto, the state that actually block encodes the Hamiltonians. In this case, it's the Hamiltonian, it's the projector that projects onto the G state. So the G state itself, and so by the way, notice that first of all, you can realize this particular conditional phase by using an ancillary qubit initialized in the 0 state, doing this conditional NOT gate, applying an RZ gate, and then undoing the conditional NOT gate. This is precisely the kind of phase kickback kind of technique that we saw, several slides earlier. Okay, all it realizes is that at the end of this circuit, this qubit is still going to be in the 0 state, and what you've done is you've sort of kicked back a phase that produces precisely these phases. On the part that belongs to G and e to the minus phi on the part that, is orthogonal to it. So, okay, but how do we actually construct this projector? Well, we know it's a projector on G, and we know how to prepare G, right? Because G is just given as U prep times 0, right? So now all we need to do is we need to do this reflection operator, or rather this projector that includes those white circles and all the qubits, right? So it's conditioned on all those qubits being in the 0 state and then applying a NOT gate. And then I'm just sandwiching both of these with a UPrep dagger and a UPrep. And I wanted to be explicit about, the fact that this is actually what I'm doing. But in fact, of course, when you actually implement this on a device, you would want to, notice that UPrep times UPrep dagger over here are just going to compose to the identity, so you don't actually, do anything in this part. But just to be sort of pedantic and explicit about it, this is the way it sort of decomposes. Okay. Okay, so now the way to apply this to Hamiltonian simulation is to first of all just split up the the exponential e to the minus IHT as a cosine and a sine. And then use this so-called Jacobi-Anger expansion, which is in terms of Bessel and Bessel functions and Chebyshev polynomials. And the nice thing about this kind of expansion is that it has definite degrees and parities, right? which is something that you needed to satisfy the conditions of the QSVT, or rather actually the quantum eigenvalue transform. And so, again, you need to truncate it, of course, to some order. But the idea is that if you can somehow realize these particular polynomial transformations of H, and this is what is signified by these two particular boxes, then you can just do the LCU method and combine those two operations. In this case, the LCU is rather simple because you only have two terms, right? And so you only need a single qubit whose prepare circuit is actually very straightforward. It's just applying the Hadamard gate, okay? You prepare the Hadamard gate and condition on this qubit being a 0. You do the quantum eigenvalue transform for cos HT, and conditioned on this qubit being in the 1 state, you do the eigenvalue transform for minus I sine HT. And then you do UPrep dagger. And basically, like after that, maybe you can use, robust oblivious amplitude amplification if you need to, but you can also post-select, depending on your needs, I guess. Or, but basically, now we're basically done, right? Like, I mean, remember, if I go back for just a second, so here, let's assume that we're working with an even degree polynomial, right? Well, if the degree is d, then basically I need like, 2 times d many calls to u, right? And so that defines what the query complexity of this technique is, right? So k prime, which basically, I mean, is the truncation parameter, also tells me the degree of the polynomial that I'm interested in implementing. And that degree, like we just saw, goes as the query complexity, and it can be shown that if you want to achieve an accuracy of order epsilon, then this truncation k prime has to scale as whatever this expression is over here. Okay? So now to summarize, we talked about these 3 different approaches to Hamiltonian simulation. I would like to call your attention to the following sort of pattern, right? So we started off with what was perhaps basically the simplest way to implement Hamiltonian simulation, trotterization, and it had some dependence on T and epsilon. But we actually, we mentioned the no fast forwarding theorem, which basically limits how much better you can do in terms of your dependence on T, but you can do better in terms of your dependence on epsilon, okay? And as we go from trotterization to LCU to QSVT, we do progressively better in our dependence on epsilon, because over here, we went from here to here, as like, instead of like 1 over polynomial of epsilon, now we have nicer scaling in terms of the log of 1 over epsilon. But this dependence was still sort of multiplicative in T and this function of epsilon. And now when we finally go to QSVT, this dependence becomes additive, right? And QSVT right now is really kind of the state of the art. As far as I'm aware, there's no better algorithm for Hamiltonian simulation in terms of asymptotic complexity than QSVT. Yes?
I think it's, you mentioned that it has optimal query.
Yeah, exactly. But I mean, there is a catch, right? Because I talked about query complexity. One thing I did not talk about is what the phi's are, right? So you need to also figure out, like, for your particular transformation, what those angles phi's have to be. Remember that the theorem only tells you that there exists some tuple of phi values for which this is true, but you have to do some numerical work in practice, to actually like achieve your target. So, this is something that I'm personally excited about. I think that you guys should certainly explore it as well, particularly in the kinds of, problems that perhaps you might be interested in, whether you're coming from a high energy or condensed matter background. I think it's a very fertile time for, the set of ideas in quantum computing and information, and the set of ideas in, kind of more traditional physics fields to sort of blend. And I'm very excited to see what you guys will do, when these things combine together. So here's some references for you. Seth Lloyd, in his 1996 paper, really, like, that paper was the first one to describe the trotterization technique to use, to perform quantum simulation. Suzuki and his higher order formulas appeared in a number of papers back in the early 90s. That paper in the middle by Nathan Weeb and Andrew Childs was really the first one to describe the LCU technique. And the particular one that we discussed today of applying LCU to the Taylor series expansion, that was talked about in this paper by Barry et al. And this last reference over here by Ike Chuang and others, this is a very nice pedagogical review of the quantum singular value transform. I will also mention, I really liked reading through Anirban Chaudhry's PhD thesis on, on quantum simulation as well. It has a nice review of some of these techniques. I talked about the uniformly controlled rotations, which was used as part of the UPrep circuit in LCU. That's this particular paper. And finally, I've been mentioning quite a bit that if you have a C to the n naught gate that you can implement in an order n operations. So Craig Gidney, who now writes papers but used to write blogs on his website, algosur.com, wrote this very nice series of blog posts starting with that one. And in this particular one, he showed that you could do C to the n naught using order n Toffelees and an answering bit, but you could do a Toffele with like 6 C naughts as well. So it all works out. So highly recommended reading, and I guess I'll stop there. Those are my email addresses. I don't have access to my NASA email while I'm abroad, but shoot me an email maybe in a week or so, and you can certainly reach me at my USRA email address as well. So thanks again for listening. Thanks again for having me here.